In this video, we'll do a recap on simple harmonic motion. Okay, do note that this is not a replacement for reading your notes, so please read your notes as well. Here I'll just give a summary on the important ideas and relationships and equations within the topic itself. Right, so just to recap what simple harmonic motion is, we can look at a case of simple harmonic motion whereby we have a spring attached to a mass, right, and at this position, which is my equilibrium position, there's no net horizontal force on the spring, right, so ignore this F for this moment, right. So this is a position where there's no horizontal force because the spring is neither stretched nor compressed, right, so it does not exert any force on the mass, right, and initially the mass is stationary, right, so this is my equilibrium position. Okay, so if I were to give this mass a certain velocity towards the left, alright, how do I do that? I exert an instantaneous force, F here, so that's what this F is about. Okay, I exert instantaneous force on the block of mass towards the left. This will give it an instantaneous velocity at this position, right? So as the mass moves towards the left, okay, the spring starts to push the mass towards the right, right? It exerts a rightward tension force on the spring, on the mass, right? So as the mass is being accelerated towards the right by this force over here, it starts to slow down until I hit zero velocity, where all the Ke has become elastic potential energy in the spring. Then I start moving back towards the center. At position C, alright, I have the same speed as position A, but different velocity because the direction is opposite to the velocity at A. Right, so just note that the velocity at B is 0. Okay, and this is where I can also find my amplitude, right, the maximum displacement from equilibrium position. Okay, so at C, I'm starting to move towards the right. Again, I go towards the extreme position, which is another displacement, which happens to be the same value as this displacement over here. So this is maximum displacement, so I call it amplitude, right? This is also amplitude. Okay, here I have velocity equals 0, similar to case B. For case D, the elastic potential energy is maximum, the K is 0, right? Then you should know I move back to E, where I'm exactly the same as A, right? Same velocity, same direction, same magnitude of velocity, right? Basically, E is a exact copy of A, right? If I were to plot out this motion in a displacement time graph, it will look like that, right? This will be position A, right, where I'm at 0 displacement. This will be position B, when I'm at my amplitude or maximum displacement from equilibrium. This will be C, D, and E, right? Why is this negative? Why is D negative? Is because in this case I took leftwards to be positive, right? So this is positive displacement, this will be negative displacement, that's why D is at this position, right? So having understood that, okay, we can ignore this F now. Okay, this F is instantaneous, so once it gives the mass velocity, this force disappears, right? Okay, so this force is not involved in simple harmonic motion at all, alright? I'm just telling you how to start simple harmonic motion. Okay, so having this graph over here with a sinusoidal shape, can I come up with an equation from the graph? Of course I can, right? This is a positive sine graph, and I sine omega t, where omega is 2 pi over capital T, where capital T is the period, which is this value over here. Okay, why is this? Why is A to E period? Because realize that this is time for one complete oscillation, right? I come back here, come back to this position, where this position is the same as this position. So the time taken from A to E is one period, right? I can call this capital T, which happens to be this capital T over here, right? So the same T as this T. Okay, if I were to be interested in my velocity time graph, okay, I would differentiate this equation over here. Okay, x equals x naught sine omega t, and that will give me v equals to x naught omega. This omega comes from differentiating sine omega t. Okay, I'm differentiating with respect to t, right? So sine omega t, when you differentiate, becomes omega cosine omega t. And this gives us one of the formulas that we can sometimes use in MCQ, which is V naught equals X naught omega, right? Why? Because realize that this value over here is my maximum velocity, because the maximum value of cosine is 1, right? So this must be maximum velocity, and this also gives me the amplitude of my Vt graph, right? So omega x naught is this value over here, and this is also equal to V naught, right? Likewise, I should have a period here which is exactly the same as this position E, right? So this is position E, okay, this will be position C, and so on and so forth. I won't draw the rest. Okay, so what else should I mention? How do I know the shape of the graph is this manner? It's because this positive cosine, so it should be a positive cosine shape. Okay, I can differentiate one more time. You should know what to do by now. When you differentiate cosine omega t, you get negative omega sine omega t, right? So the negative, I leave it here. The omega that comes out of differentiating cosine omega will multiply into this omega here, give me omega squared. Right, so I get A equals minus omega squared x naught sine omega t. Okay, again, I can draw the graph of negative sine, right? Where did this negative come from? It comes from differentiating cosine. Alright, so I also know that this part is my amplitude again. So this is omega squared x naught, which is the amplitude of my graph. Alright, and of course, if I were to be more accurate, this would be period again. Alright, so if you're asked to sketch any velocity time graph or acceleration time graph, try and make sure these values are included as far as possible, or as far as the question allows. Right, so with these graphs, we can come to a few nice conclusions. One, we know that this is true. V naught equal omega x naught, right, because of this part over here, right? X naught omega realized is the maximum value for V, right, which is V naught, right? So V naught equals to omega x naught, right? This is always true for any SHM. This, however, is not true, right? So please be careful when you use this equation, right? This is okay. The maximum velocity equals omega times maximum displacement, but V is not equals to omega x, right? If you look at V is some value times cosine omega t, x is some value times sine omega t, right? There's no way to make these two things the same with just a constant, right? So this is definitely not true. Just be careful not to use this. This is true as well. Why? Because if I look at this equation, it actually comes from here, right? Minus x naught omega squared. This x naught omega squared is actually a naught, right? So that's how I get this equation. So this equation is true for all cases. And how do I get this final equation? Right? If you compare a and x, do you realize that x naught sine omega t is actually x, right? So if x naught sine omega t is actually x, then I can replace x naught sine omega t by x, and what's left over? Minus omega squared, right? So a equal minus omega squared x, and this is a general case. It's true for any SHM, so this is correct for any SHM, right? So this is unlike this case. This case is not true. This general equation is not true. This general equation is true, alright, and you should realize this is the defining equation for SHM, right? Meaning if you want to define SHM, you have to do it in words, but in essence, it represents this equation's meaning, right? So yeah, with that, I will end this video. Okay, this T here just represents that the tensional force exerted on the mass is towards the right, and at this position, the tensional force acting on the mass is acting towards the left.